All right, welcome to day 6. Homework is day 6 textbook problems. We're going to go through each of the homework questions one by one in the worked out answers. So I'm just going to flip right over to them. So in 16, we wanted to be comparing to 1 over 3 to the n. Now 1 over 3 to the n is the same as 1/3 to the n because 1 raised to anything is 1. And that allows us to see that it actually is a geometric with absolute value of r less than 1, so that would be something that converges. So if we do our limit comparison test, dividing our original and the 1 over 3 to the n, keep change flip makes the 3 to the n go on top. As n goes to infinity, that minus 5 isn't going to do anything. So we essentially have 2 times 3 to the n over 3 to the n, so it's really 2 over 1, so that's approaching 2, which is a positive finite value. So that means that our original series will do the same as our nice series. We already showed the nice series converged, so we just say by limit comparison test, write that original series and say it converges. Now, when you're doing direct comparison test and limit comparison test, it is important in that concluding statement you're clear which series you're saying converges or diverges, because there's multiple series that you're looking at in the problem, your original and your nice one. If it's something like, say, P series, you can just say converges P series where P is greater than 1, and that's fine. You don't have to restate the actual series that you were talking about because there's only one you're working with. But in direct comparison and limit comparison, there's going to be multiple that we're talking about, so be clear in your final statement which series you're talking about. Going over to 18, a square root of an n squared is essentially going to end up as an n to the first, so we want to compare with the series of 1 over n. 1 over n is either harmonic, you can think of it as, or a p series where p is equal to 1, so therefore that diverges. When we divide, it's like multiplying by n, so we get a 3n on top. Well, as n goes to infinity, that minus 4 is not doing anything, so that's really like saying square root of n squared, which is absolute value of n. But because we're going to a positive infinity, that's really just n, so the n's wipe out and that goes to 3. 3 is a positive finite value, so therefore our original series does the same thing as our nice series. So we can say by the limit comparison test, our original series there diverges. For 19, the gap in our exponents is 3, so we'll compare to the series of 1 over n cubed. Both those are positive. Now, you don't necessarily have to state this, but you need to at least check in your head that it's true, because limit comparison only works as long as the series are positive eventually. So you need to at least think about it, but you don't necessarily have to write that bit. When we divide our two expressions with keep change flip, an n cubed will essentially get distributed through in the numerator. Then we've got same degree, so it's ratio of leading coefficients. We get 2/3. That's a positive finite constant. Our nice series, the 1 over n cubed, is converging because we got a p series with p greater than 1. So therefore, by limit comparison test, our original series will also converge. 21, if we distribute the n on the bottom, that's n squared plus 2n. So we have a gap of n to the first. So we'd want 1 over n to be our comparison. When you divide and do your keep change flip, an n essentially gets distributed through the numerator. Same degree, ratio of leading coefficients is 1. 1 is a positive finite constant, so limit comparison test tells us that our series will do the same as the nice series. The nice series, you can either say it's a p series where we got p is greater than 0, less than or equal to 1, or you could just say it's the harmonic series. Any of those are fine to say that it diverges, and therefore our conclusion is by limit comparison test that our original series also diverges. For 23, the square root of the n squared part is kind of like an n. So it's like we have an n times an n in the denominator, or an n squared. So we would want to compare with 1 over n squared. When you divide and do your keep change flip, the n squared gets multiplied on top. kind of like we saw in the other one, the square root part, as n goes to infinity, the plus 1 is going to be inconsequential. The square root of n squared will be absolute value of n. And what I did from this step going to this step here is I also just divided the n's out here, so we didn't have to worry about those. If you didn't do that, then you would have had n squared over n squared. But eventually that goes to 1, positive finite constant, so our limit comparison is applying. Our nice series that we were using to compare is a p series with p greater than 1, so that's converging. And therefore, by limit comparison test, our original series is converging. Now, you have to say by limit comparison test for these. For 24, basically the n's were already matching up, so we needed to get a 2 to the n minus 1 to match up as well. So we'll have 1 over that. When you divide, that 2 to the n minus 1 multiplies in the numerator. The 2 to the n minus 1s will wipe each other out. Then same degree, ratio of leading coefficients gives us 1, which is a positive finite constant. So our nice series can be rewritten as 1/2 in parentheses to the n minus 1. That's geometric with an absolute value of r being less than 1, which means it converges. So by limit comparison test, our original series also converges. For 26, the square root part, again, the plus 4 is going to be inconsequential, so that square root of the n squared is like an n plus an n is like a 2n. So think of like the denominator, our target's going to be roughly a 2n, so we're missing an n in the numerator. So we want to compare to 1 over n. When we divide, multiply by the reciprocal, you get n on top. So the bottom, again, we said was going to head towards 2n essentially. So same degree, ratio leading coefficients, you get 5/2. That's a positive finite constant. Our original series was our harmonic one. You could either say it's harmonic, so it diverges, or talk about it being a p series. And that's why it diverges, because we got a p that's greater than 0 but less than or equal to 1. And then by limit comparison test, our original series diverges. For 27, this one was probably tricky. So what we're going to do is we're going to compare it to 1 over n, which we've seen several times is diverging because it's harmonic, or p series with p greater than 0 but less than or equal to 1. When we divide here, we're not going to do keep change flip. So we're looking at this part right here. As n goes to infinity, 1 over n is going to become small. So this limit could be rewritten as x approaches 0 and make the 1 over n's just be x's. These two limits should be the same because in both cases it's sine of a small over a small. Well, now that limit's more familiar, we know that goes to 1. Because that's a positive finite constant, our original series diverges as well by the limit comparison test. All right, the next set, we needed to use one of each of these as you were going through. I divided out a square root of n, turning that to 1 over n to the 1/2. So then that's a p series that diverges because p is greater than 0 but less than or equal to 1. 31, I compared to 1 over 3 to the n. When you add in the denominator, you're dividing by something bigger, so it makes the value smaller. So my 1 over 3 to the n, I rewrote as 1/3 to the n, which makes it a geometric that converges because absolute value of p is less than 1. So therefore, everything smaller than it will also converge. Well, we just talked about how that is always going to be smaller, so therefore by direct comparison test, our original series will converge. And I guess I skipped over 30, but 30 is just geometric with absolute value of r less than 1, so that converges. 32 is kind of like the first half of the homework. We could compare it to 1 over n squared. When you divide, do keep change flip, you get same degree. Ratio of leading coefficients is 1/3 as n goes to infinity. That's a positive finite constant, so limit comparison test is going to apply here. The nice series was a p series with p greater than 1, so that converged. Therefore, by limit comparison test, the original series converges. Now, every time I'm saying this out loud, I'm just saying the original series. You can't write, like in words, the original series. You've got to actually write out the actual series when you're saying that. Just rather than reading out all the n's and stuff, I'm just calling it the original series as I talk about it. 33, as n goes to infinity, we've got same degree, leading coefficients is 1/2. So if when n goes to infinity, your individual terms of the series are, if it's not going to 0, then that automatically diverges, and that's nth term test. In 34, if you write out a couple terms, you see that things will start to wipe out. There's only one term that doesn't wipe out on the front, so we should have one term on the back end that doesn't wipe out, so a minus 1 over n plus 2. As n goes to infinity, that second fraction goes to 0, so therefore this goes to 1/2, meaning it converges, and we did telescoping here. 35, it's positive, continuous, and decreasing, so we can switch that to an integral and make the n's x's, and we'll do an improper integral going from 1 to infinity. I jumped right into doing the limit and didn't show the infinity part. Then you can do a little u substitution with a correction of 1/2. When doing the u substitution, changing your bounds to 2 and b squared plus 1. Antiderivative is negative 1 over u. Fill in your b squared plus 1 and 2, which that's going to be up on the top right here now. So I'm going to scroll up. Once we fill those in, let b go to infinity. The first fraction goes to 0, so this ends up as a 4th. So this converges by the integral test. Important to remember with the integral test, the value of our series is not 1/4. The integral test, by it converging, only tells us that the series converges. The only series that we can actually find the real sum of it are telescoping and geometric. Any others, we're just using tools to decide if it converges or diverges. It is very common on the AP for them to show that you have an integral test, you end up getting 1/4 as the answer, and then it'll say which conclusion is valid. One of them will say that the value of the series is 1/4, which is not true. We would want to say that all we can conclude is that the original series converges. (36), we could do another limit comparison test with 1 over n squared, because by this point we've checked all of them off. 1 over n squared p series with p greater than 1, so that converges, so the original series also converges. And 55, so this said, if a smaller one converges, then a bigger one has to diverge. So if we're going to prove this false, we would need to have a small one that converges and one that's bigger than it that also converges. So I picked my small one as 1 over n cubed, because like say if you put 2 in, that's 1/8, and then the big one, 1 over n squared, that'd be 1/4. Well, the bigger one is still a p series with p greater than 1, which will also converge. So therefore, this proves this false, because you can figure out ones that are bigger than it that will still converge. Just don't get too small with that exponent. You don't want that n's exponent to get anything 1 or smaller, because then it would switch to a diverge. All right, today's topic, we're going to look at a new test. It's the alternating series test. So first, a recap of what it means to alternate, and this is in our day 6 in our notes packets. So alternating series is just when the signs of the individual terms are bouncing back and forth between negatives and positives in either direction. Two common ways to show that. So notice we have the negative 1 to the n. If n is starting at 1, that would start us out with a negative. If we had to the n plus 1, though, or say to the n minus 1 for that negative 1, that would start us out with a positive. Going down further, we've got a negative 1 to the n here. Notice this is essentially a geometric where we're multiplying by negative 1/2, and it's just showing that we are alternating signs there. So our alternating series test. An alternating series, okay, so it has to be switching signs, will converge if these two things are true. If an plus 1 is always less than or equal to an. So what's meant by that? An plus 1 is the next term. So if the next term is always going to be less than or equal to the current term, that will help lead us to an alternating series converging. That's one of two criteria. Now, when we say the next term is less than, sometimes it might take a few terms for that to happen. So what this is saying is basically eventually that's true. Sometimes maybe you'll sub in 1 and 2 and 3 and that's not true. But then from 4 on, the next term will be less than the term before it. So as long as that's eventually true. Now, the second one is the individual terms. So that's what an is. As n goes to infinity, the value of the individual terms has to go to 0. Now, a reason that that makes sense is if that second thing is not going to 0, that's something we've seen that it's an automatic diverges by the nth term test. For any series to converge, the individual terms have to go to 0. Now, what we mean by an is the terms in our alternating series, but ignoring whether they're plus or minus, just looking at the positive version of them, or think the absolute value version. So we're looking at the magnitude of them and not necessarily their sign. If those two things are true, then we can say it converges by the alternating series test. Now you have to physically show that you're checking those and that they are true for us to use the alternating series test. So first off, we want to recognize we got that -1 to the n, so this is going to alternate. So we want to trigger in our brain, well, let's check the alternating series test. So we've got to think about, will the next term always be less than the term before it? If you're ever unsure, just sub in a couple values of n. When we sub in 1, we're going to get -1. When we sub in 2, we'll have a positive and we'll get a half. When we sub in 3, we'll get a negative and we'll get a third. And notice it is going to keep getting smaller for each term. So we'll check that off. Are the individual terms approaching 0? Well, as that denominator keeps getting bigger, they will approach 0. So we can check that off. And so we can now just make our conclusion. So therefore, we can just say, because there's only one series, we can say therefore converges by the alternating series test. This is a really popular test. One, because it's pretty easy, and it's also easy to recognize when it might be able to be applied because you've got the alternating signs. Now in these examples that we're giving, at the start here, I am already having our two conditions written. On like a test or something or your homework, you're going to actually write out those conditions and put check marks to show that you've thought about them in order to confirm that we can even use the alternating series test. All right, going over to the next page, we've got a new series. If we write out a couple terms just to see what's going on, when we sub in 1, we're going to get a negative. And we'll have 1 in the numerator, 2 minus 1, 1 in the denominator, so we'll have -1. Next one will be positive. When we sub in 2, we'll get 2 over 4 minus 1, so we're going to get 2/3. If we do one more, we'll get -3/5. So is each successive term less than the one before it? Well, we've got 1, we've got about 0.66, then the next one is 0.6, and so on. So it does look like they are getting smaller each time. And our individual terms getting to 0? Well, let's see. If we've got our ratio of or we've got the same degree, so ratio of the leading coefficients, this would actually not go to 0. It would go to 1/2. So category 2 did not apply. If your individual terms are not going to 0, this automatically diverges by the nth term test. So what's great about alternating series tests is if that second condition fails, you're already done with the problem also because you'll be able to say it diverges by the nth term test. Now, if you are totally stuck about if the terms are getting smaller than the one before it, one thing you could do is think of it as a function, do the derivative, and we would need the derivative to be negative. Notice when we do this derivative, we do a little quotient rule. We get -1 over that quantity squared. Well, the quantity squared is going to be positive, so the top is always negative, so this would always show that f of x is decreasing. That's just if you were stuck. Usually, though, I would say just write out a couple terms, and it should be not too bad to think through that the terms are getting smaller from one to the next. All right, next page. What's nice, we've got the terms already written out for us. We want to recognize that it is an alternating series. So let's check out the alternating series test. We'd want to see is each successive term less than the one before it. And remember, when we're talking terms, we're ignoring the negatives. We're just looking at the absolute value of them. Well, here's an example where the first two terms, they are not getting smaller than the one before it. It's exactly the same. And that's okay. It's equal to in this case. But also just remember, I mentioned on the first look at the alternating series test that eventually the terms have to be getting smaller. And these do. 3/4 is like 0.75, 4/8 is a half, and so on. So those are getting smaller. So this one checks out. Again, on your homework, you're going to have to physically write an plus 1 less than or equal to an. Think about it, and then if it's good, do the check mark. And then you'll have to write out your limit. Now, when you write it out on your own, it is okay to do limit as n approaches infinity and just call it an, and then think about it. Does it equal 0? So let's think through this one. We've got an exponential in the denominator. We've got an n, or you can think of it as a polynomial in the numerator. We saw in Unit 6 that exponentials will always grow more quickly than anything that's polynomial or a power. So therefore, bottom's going to get bigger much faster. So this will go to 0. So that does check out. Now, you have to actually think through those and not just automatically check them, because if it doesn't satisfy those conditions, then saying it converges by alternating series test would be incorrect. But these did check out here, so we can say converges by alternating series test. Moving down to the bottom, we've got the terms already written out for us. It is alternating, so we would want to think, let's try the alternating series test. Each successive term is less than the one before it. The terms are heading to 0 because the denominator is going to keep getting bigger and the numerator staying at 1, so that checks out. So therefore, we would say that this converges by the alternating series test. So as you can see, alternating series test is one of the easier tests that we will see. And again, it's pretty easy to recognize because of the alternating signs. Now there's one more part for today, and it's called the alternating series remainder. Let's say we have the alternating harmonic series. So alternating but 1 over n. Now, one thing just to talk about, it is alternating. Notice each term is smaller than the one before it, and it's heading to 0. So this series would converge by the alternating series test. So the alternating harmonic converges, but the regular harmonic series is a diverge, which is something that's pretty interesting. So what this is saying is the S represents our infinite sum, the one in green there. So our sum from 1 to infinity. Sn represents the partial sum. So let's say we do the sum of just like the first 10 terms. Whatever is left after those first 10 terms, let's say, we call that our remainder. So it's all the leftover stuff that we would need to tack on to give us our, um, our infinite sum. Well, let's say hypothetically we did go to 10. Our remainder would include things like, let's see, the evens are all positive here. So our remainder would include things like negative 1 over 11, oops, 11, plus 1 over 12, minus 1 over 13, plus 1 over 14, and so on. Well, what happens here? Let's say you start with negative 1 over 11. And I'm just going to draw a number line to help us visualize this. So let's say negative 1/11th is here. And we're just focusing on the remainder terms. So that first remainder term is negative 1/11th. Well, if I add on 1/12th to that first remainder term, 1/12th is, its absolute value is a little bit smaller than 1/11th. So basically what will happen is by adding them together, it's going to put our remainder somewhere around here. Well, then the next thing we're going to do is we're going to subtract something off. Well, if you subtract off 1/13th, that's going to move us back to the left on our number line, but it's not going to take us as far as negative 1/11th. So maybe it's going to put us like somewhere here. And then when you add 1/14th, that's going to make us a bit more positive, but it's never going to take us all the way back to 0, so maybe it's going to go here. And as you keep adding on terms, the total sum of that remainder is just going to kind of bounce around in this area here. Well, notice at all times, as we keep adding on an infinite number of terms, that remainder is going to stay between negative 1/11th and 0. So something we know is true is the entire value of our remainder, once they're all added up with their pluses and minuses, is guaranteed to be less than or equal to the absolute value of just that first next term. And that's what the remainder theorem is saying here. Our remainder in general, the absolute value of the remainder, if you take the infinite sum and subtract off the partial sum, it's guaranteed to be less than or equal to just the next term. Now, we just care about the absolute value of it. We don't care about the plus and minus. So you are guaranteed that that next term, that is an upper bound of all the extra stuff that we're not including when you combine it with the pluses and minuses. So in this particular series, S5, if we did it, so that would be the sum of the first 5 terms, would be negative 47 over 60. So that means that our absolute value remainder of the 5th term, which is the same as saying our infinite sum minus the sum of the first 5 terms, we're guaranteed that that's going to be less than or equal to the value of the 6th term. And again, that's without the plus or the minus, without the minus, just the absolute value of it. Well, our 6th term, because we had 1 over n, is just 1 over 6. So this is saying, basically, our remainder is guaranteed to be less than or equal to 1/6. So in general, if an alternating series question asks for the maximum error or the upper bound of the error, it's just the absolute value of the next term. That's all it is. Because the absolute value of that next term will be greater than or equal to any combining of all the leftover terms, because they're going to add a little bit less, subtract a little bit less, add a little bit less, subtract a little bit less. And it'll basically just whittle away from that original first remainder value, like our 1/11th that we had in this case. Just so you can get another sense of what this is really telling us, this is telling us that our infinite sum is somewhere between negative 47/60 minus 1/6 and negative 47/60 plus 1/6. Because that 1/6, that next term, is our maximum error. So we didn't care about the sign, so that could have been either added or subtracted. So, but we know that negative 47/60 is within a sixth of the infinite sum. And why that is powerful is, well, if you think when you're computing, if you were computing these by hands, eventually when you get out really far, it's not changing the sum by much. So you might have an idea in your head, okay, I'm going to do these out until I know that it's within a certain threshold of the infinite sum. Well, that threshold would end up being your remainder. So as long as that next term is close enough to how you want, then you've taken the sum out far enough and given that infinite sum a good enough approximation. All right, one more question for today. So we've got a infinite series here. We want to find how many terms do we have to go out so that our partial sum, our Sn, is within 0.001 of the infinite sum. Well, a couple ways we could do this. We could just look at the individual terms, find the first one that is 0.001 or less. That'll be the error term, so we should carry out our series to the term before it. You could do that, but we might have to go a really long ways. Like 4/24 is not close to 0.001 yet. So that's one option of how we could do that. Another option, and we'll come back and look at that first option after we do the kind of algebraic way, is let's take our series but without the minus, so 4/n factorial, and we can just look at that in a graphs page. We'll have to put x in instead of n, and see what's the first y value, essentially, that is 0.001 or smaller. Whichever one is 0.001 or smaller, that'll be the error term. So we'd want to go out to the term before that, because remember, the error term is always the next term. So let's go over to our calculator page, or sorry, graphs page on our calculator, and we're going to do 4/x factorial. Now the factorial button, if you're unsure, is over next to the G. So right of the G, you've got all these templates. Put your factorial in, hit enter, and we care about the table. So at 1 we've got 4, 2 we've got 2, then we got 0.66, not there yet. We're looking for 0.001 or smaller. So not there yet, not there yet. Well, notice if we just look at the table, it goes from 0.005, which we're getting closer, but not 0.001 or less yet. And then it goes to 7.9. So this is what you got to be careful with in your table. If I scroll down one so we can see that value, and mine, I think on yours it'll show it all the way out down there. But if we go down to the bottom, notice that's E negative 4. So E negative 4, that's scientific notation. So let's think what 0.001 is in scientific notation. If you move that over 3 times, that's really 1 times 10 to the negative third. So we need something that's smaller than 1 times 10 to the negative third. So any exponents that are bigger negatives than negative 3 would be it for us. So this is our first one that is in fact smaller than 0.001, or in other words, 1 times 10 to the negative 3. We got 7.9 times 10 to the negative 4. So that means this is our error term, meaning we'd want to go out to the one before. So how we show this for our work is we would show a little t-table. So we would have n and we'd have 4/n factorial. And you've got to show at least 2 values. So I'm going to show 6 and 7. So at 6, we had 0.0055, dot, 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 dot. And for 7, This was to the -4. So that's going to be 3 zeros and then the 7, 9. And then what we'd identify is that this is the error term. Well, the error term is your next term, meaning we would want to carry this out to the 6th term. So we would want n to equal 6 to be how far we want to carry it out. Error term in an alternating series is your next term. We wanted that next term to be less than 0.001, so we just put our series in a graphs page without the minus, and we find which is the first one in the table to do that. Now, the other way we could have done this is we could have continued. We'd have 4 over 24 is really the 4 factorial. So we would have 5 factorial, and that should have been a minus probably there. Then we would have plus 4 over 6 factorial minus 4 over 7 factorial. And we would just type these in individually and see what's the first one that is less than or equal to 0.001, and that would identify our error term. Well, we would find that this one is the error, so therefore we need to go out to this term, which was when n is equal to 6. So 2 different ways you can go about it. The reason the calculator way is better is what if you got to go out to 1,000 terms? You're not going to want to write out 1,000 terms to do that, but we could scroll through the table to eventually figure that out. All right, that's it for this video. Any time left in the period, you're welcome to start your homework. Have a good rest of your day.